Moreover, as Nicholas Copernicus presented the heliocentric model, one more staggering difference in the way we could interpret the universe could arise, igniting a discussion known as the emergency of cosmology. This emergency is set apart by tremendous contrasts in our evaluations and understanding of the universe's key properties, such as its age, size, and rate of expansion. Neil deGrasse Tyson has observed that the discovery of the James Webb Space Telescope, JWST, has reignited this discussion with images that challenge the known laws of physics. All things considered, what exactly is this emergency, and how does the James Webb Space Telescope contribute to it? To say it contributes is, in fact, a bit misleading. More precisely, a re-examination has been underway. The emergency points to how our understanding of the universe is being tested, particularly in terms of its age and size, which are primarily areas of uncertainty. The deployment of the JWST has been crucial in this context. Before this state-of-the-art development, our ability to see into the early universe was limited. However, with the JWST's advanced capabilities, cosmologists can explore much more distant galaxies, providing new perspectives on the universe and challenging some of our previous assumptions. This progress allows us to peer further back in time, closer to the Big Bang, and observe galaxies as they were forming, providing essential data that can either support or challenge our current models of the universe. To understand the emergency comprehensively, it is essential to first review the standard model of cosmology, known as the hot inflationary Big Bang model, or lambda cold dark matter, lambda CDM model. This model has been remarkably successful in explaining various aspects of the universe, from gravitational lensing to the formation of the cosmic web and galaxy clusters. The lambda CDM model posits that the universe began with a massive explosion, followed by a period of rapid expansion, and has been expanding ever since. It incorporates elements like dark matter, which exerts gravitational forces, and dark energy, which drives the accelerated expansion of the universe. However, every new observation, especially those from advanced instruments like the JWST, raises the possibility that our current model might be flawed or in need of revision. The lambda CDM model makes specific predictions about the characteristics and behavior of galaxies at different stages in the universe's history. For instance, it predicts that galaxies in the distant past should be smaller, less developed, and composed of fewer heavy elements compared to those we find in the nearby universe. This is because heavier elements are formed in the cores of stars and distributed through processes like supernova explosions, which take time to occur. The situation described concerns how the standard model of cosmology predicts the evolution within clusters of galaxies and the properties of the cosmic microwave background, CMB. According to this model, galaxies in the distant past should be smaller, bluer, less evolved, and less rich in heavy elements at greater distances compared to our own. This would lead us to expect periods of the universe without observable stars or galaxies. However, scientists have found unexpected evidence that challenges these assumptions, leading to what is being termed a crisis in cosmology. The crisis in cosmology revolves around uncertainty about the age of the universe. Different measurement methods yield different results, forcing cosmologists to grapple with these inconsistencies. To address this issue, scientists use several approaches to determine the age of the universe. One method involves studying the cosmic background radiation, which traces the universe's expansion history using mathematical models like the Friedmann equations based on Einstein's theory of general relativity to calculate the expansion rate and, consequently, the universe's age at different epochs. The CMB, a remnant radiation from the early universe, is a crucial tool for this analysis. Detailed maps of the CMB, such as those provided by the European Space Agency's Planck mission, offer valuable information about the universe's consistency. Despite these maps lacking data on dark energy, a significant component of the current universe, scientists can use the Friedmann equations alongside various observations to measure the universe's expansion rate and ultimately its age. The Friedmann equations describe how the universe evolves, accounting for the density of different components like dark matter, dark energy, and ordinary matter. By studying the CMB, scientists can reconstruct the conditions of the early universe and extrapolate its expansion history up to the present day. Another approach to determining the age of the universe involves observing exploding stars, specifically type Ia supernovae. These supernovae act as standard candles, allowing cosmologists to measure distances in space. Candles, since they have a known natural magnificence, can differentiate their known magnificence from their bright brightness. Cosmologists can choose their distance and, subsequently, the universe's advancement rate. At different times, this strategy used during the 1990s played an essential role in the discovery of dark energy, which is currently key to cosmological assessments. It is particularly useful for determining the Hubble constant, a measure of the universe's rate of development. Though not thoroughly consistent, the Hubble constant is instrumental in charting the universe's development since the Big Bang, approximately 13.8 billion years ago. It has been observed that the universe has been consistently expanding. NASA has noted that the implications of this rate are critical. If the advancement is slowing down, it suggests the presence of dark energy may be influenced by dark matter. Conversely, if the expansion rate is speeding up, it could indicate the presence and effect of dark energy, accelerating the universe's improvement. In January 2018, scientists found something captivating. Two telescopes showed that the universe's expansion rate varied, depending on the observation point. The Gaia Space Telescope assessed a faster advancement in a nearby universe, while the Board telescope estimated a somewhat slower advancement in more distant areas. This assessment discrepancy highlights the universe's vast size and reminds us of Edwin Hubble's pioneering work, which proposed the universe's improvement rate in 1929. Hubble's observations of distant galaxies revealed that they are moving away from us, suggesting that the universe is expanding. This discovery was one of the foundations of modern cosmology. Regardless of your location in the universe, you would notice a similar phenomenon at a comparable speed at the Hubble advancement rate. Initial assessments relied on limited data, but with technological advances, such as the Hubble and Gaia telescopes, we have been able to observe more variables and refine our assessments. Different telescopes use cosmic microwave background, CMB, readings to calculate the constant. However, this method has its limitations due to the availability of supernovae for distant observations, which restricts our understanding of the universe. Since the discovery of dark energy in the 20th century, scientists have been puzzled by the differences between these two methods for determining the universe's age and expansion rate. As assessment techniques become more precise, more subtle variations arise, driven by the development of more advanced structures. This advancement unexpectedly raises new questions rather than providing definitive answers. Yet, the discrepancies are minor, with only about 10 to 20 million years separating the estimates, considering that the universe is around 13.77 billion years old. It indeed warrants careful examination. One potential explanation for this inconsistency is the possibility of flaws in our measurements of the CMB. Despite being one of the most precise assessments, it has been extensively tested since its launch in 2003 to validate its accuracy. Another perspective suggests a possible gap in how we interpret dark matter, raising the likelihood that it could vary over the long term and be related to dark energy or another dark component. This possibility has led to various preliminary studies on the precision of cosmic microwave background estimates. The complexity of star formation can also introduce uncertainty into the models we use. Addressing this uncertainty in cosmic expansion models could help reconcile the differences in estimates. This crisis in cosmology has also been exacerbated by the discovery of the James Webb Space Telescope, JWST. According to Neil deGrasse Tyson, the JWST found objects in the universe that challenge our current understanding. This suggests that our scientific perspective requires a complete overhaul. Yet the problem is that we have no clear indication of where to start in making sense of the extent of this scientific upheaval. We ought to explore the origins of the universe around 150 million years after the Big Bang, when stars, black holes, and star clusters began to emerge, possibly as soon as 50 to 100 million years after the event. However, these occurrences should be generally fascinating. What we don't know is how typical galaxies were at later times. Observations from the JWST reveal galaxies much more distant and, consequently, older than the standard cosmological model predicts. This inconsistency suggests that our models require a significant update. The discovery that the developing universe relied on these galaxies is a critical development. JWST images show galaxies that formed significantly earlier than expected by current cosmological models, triggering a crisis in the field. This issue relates to galaxies and redshift, which is a standard assessment in cosmology, as indicated by the Standard Model. Hydrogen began to appear,